I test for that more often. Against buffer overflows, I test for buffer overflows more often, and so on. The adjustment of that selection gets modified based off of prior results. So let's begin with the population selection. So those same pretty graphs we saw earlier are now in a horizontal fashion. We see buffer overflows on the left going over to random mutation on the right. And within there, just random test cases, or not random, but specific test cases sometimes, and random test cases sometimes, which trail off of those classes. So those are our populations that have to compete against one another. Fitness algorithm design. The goal of the fitness algorithm is to make fitness criteria accurate and determined by generally available criteria. This is where some of the blind security testing comes in, and why I focus on that as this talk. But other approaches, I mentioned before, profiling via debugging or coverage, also things that you might want to look at are log entries, system logs, stuff like that. Even in the one difficulty of going straight for the debugging and code coverage we hit on earlier on is that though code coverage is a great metric for how many tests you're running and how much code you hit, as we showed earlier with the logic flow, it's not a 100% accurate way of determining test coverage. You might be following every logic flow, but you might still have a SQL injection in there that isn't part of what you're measuring. It might be in a system dependency. And then also, it's again, if we require interactive access, it's not broadly available, and that's a question back there.
Yeah, I would say, I would think that probably code coverage would help define how much tuning you can do, because if you don't test a particular branch, you'll never see the security flaw there.
Absolutely. And I'm actually not arguing for this as being a approach that is going to be necessarily better, just more generally usable. And where it's applicable, I would say definitely the more information you can get into a fitness algorithm, the better of a selection you're going to make. Any more questions? Okay. But yeah, so that's the downside. The major downside is that if we were to optimize purely for that point, we would not necessarily have an optimum test set, and that's where a diversity of criteria come in, and then also that it's not generally available. So another design, or you could say an additional criteria, would be to use system feedback and the natural properties of test cases. So system feedback, what we can do is, as we are generating our test parameters, the requests that we're going to test, we can keep control information about each request or parameter that we're going to test. When there is nothing evil happening and I make this request, I know what the response is going to be. So when we start doing evil things, when we start putting nasty data in there, when we start making random mutations, we can identify a difference in control, and I would call that the magnitude. And also, if you have flaw-based testing, like the set of specific characters we use to test SQL injection, then we can also use more sophisticated methods of error detection. I'll go into that in a moment here. Oh, forgot the picture here. The big thing here, though, is as we're building our evolutionary system, we still have those same cases. They go into a test engine along with the request to be tested, and then the results of those tests go out of the test engine, and then feedback from the results comes back into the test engine. That's where the selection comes in. We'll talk about the selection criteria in a moment. But if we want to see how this works in the real world, consider a web application, and you capture that legitimate request. We know the control. We make a security test case. We put that apostrophe into a parameter. There's two things we're going to measure: the magnitude of change. Now, the magnitude of change would be the size of the data that is added. If we do a diff between new and old, the size of what was added plus the size of what was removed. Now, I will argue that this is a good thing to verify or to look at as a fitness criteria because it's effective, broadly applicable, and even fuzzing, we will recognize that if the system stops responding, that this is something that is going to generate a magnitude of change, whereas once it responded, it does not anymore, and that is going to say, hey, this is something bad happening, we'll check it out. Then also just think back to experience, where if any time I put in a apostrophe into that login field and I get a SQL exception back, what do I see? I see what was the original page that maybe would redirect me to my logged in console, or maybe the access denied. I'll see that page go away and I'll see a big exception trace come up. Or I'll see that page go away and I'll see a error, non-determined application thing comes up. And in all cases, not in all, but in most cases, we will see a significant magnitude of change. And this is a pretty good, broadly applicable way of determining if something requires more search. Again, this is not trying to identify the exact flaw or line of code. This is fitness criteria. It's saying what this causes more change to the system than legitimate data does. That's actually the second thing I was going to go into here. There are two broadly available fitness criteria I would say should be addressed in a blind security scenario, and we can go into others in a moment, but good question. The second one would be error detection. Now, if we're doing flaw-specific testing as some of our criteria, or our test classes, then we also understand the specific, a lot of what we should expect when it comes back. So like you mentioned, cross-site scripting. If we go and put some determined pattern into a request, ZZZZZ, and we hit reflect, then we can say, you know what, this is reflected data, let's see what we can get through. Apostrophe, quotation mark, brackets, semicolons, things that you would use to mess up the HTML document or JavaScript code that you're seeing this data reflected in. It's going to be dependent on where you see the context of where it's reflected. And you can test for that. You can see that, you know what, I'm seeing some things that I don't necessarily want to see reflected. And then you can also have that be fitness criteria. So for each of the flaw-specific tests that you put into this system, you would have a pluggable framework of this is the way you look for flaws. And so you can get very sophisticated with that as well. So SQL, for example, SQL injection, what I could do would be not only just wait for the SQL exception or the non-specific error returned, what we often see. I could start moving into blind SQL injection techniques. I could try the 10, 15, 20 different ways in which you can often complete out a SQL statement and see if you can make it return not the error but something different. And often when I'm doing blind security testing, that's exactly what I do if I want to verify. I'll start off by putting an apostrophe, and then I'll do apostrophe and then comment characters, hyphens, or the like. And if I see that happen, I say, you know what? I was able to get an exception by just an apostrophe. I messed up the SQL statement. I was able to do hyphen and get it back, and nothing. I didn't see the error anymore. So you can put a lot of intelligence into that. And the same can be said for just about everything. So then choosing the next test. So fitness criteria adjusts the natural priority of test cases. So I've hinted at this about 1,000 times already, but what happens is each suite of test cases, or for flaw-specific testing, random testing, whatever, is assigned a default probability. And when we start seeing these test cases come back successful in finding what is likely to be a fault, or we could be more general and say a major change in system behavior, then we emphasize both that test class and then make that specific test case more likely to be executed. So what we'll have is, over time, that probability shift towards classes of flaws that are more likely to be present in the application as we go on. And again, this has a major assumption that flaws tend to be shared across a large component or application. And this is a viable assumption because a lot of times these are created by the same developer or same development team with similar coding guidelines, similar technologies. So it seems like a good assumption to take, and one that helps us create broadly defined evolutionary fuzzing systems or security testing systems. So note that one thing we never do, one thing I would rather avoid doing, is to remove a test case or class of test cases. Because one of the original goals is to not simply have a SQL injection test framework. We can write one of those rather easily and not have to say anything about evolutionary algorithms inside of it. What we want to do is make it so that we optimize test sets so things that are more likely to cause flaws will find flaws, but that on occasion we still have the chance to find that random flaw based off of some random character. The end result is that cases compete for execution time, and better cases move to the top, both within classes and the classes themselves. So we go back to that again. What we see here is the same graph that we looked at a moment ago, except for we now have probabilities on there. And on this particular run of test cases, we'll see that hey, buffer overflows and format strings have been de-emphasized. SQL injection is way up there, and so is cross-site scripting and random testing. And that's just a lot of what I've seen when I'm doing general web application pen tests. Now, one thing to call out as a potential issue is test set stability. So if we were to leave this by itself, then one type of application that might cause some problems are, let's say we have two friends creating a web application. And the one really likes .NET, and the next one really likes C++. And so they create the worst architected web application ever. And half of it is susceptible to cross-site scripting and SQL injection. The other half is subject to buffer overflows and format strings. So what you would have is, as you're testing request number one, that emphasizes our friend that wrote it all in .NET or Java, and we start really skewing towards SQL injections, cross-site scriptings, and other things like that. And then as we moved over to the friend that wrote all in native code, we'd start seeing all these buffer overflows, and we keep on going back and forth. And actually, it wouldn't be terribly efficient because we'd have to do the build time on each request to actually recognize that things are more likely to be buffer overflows and move it over there and go back and forth. So one option is to reduce the temperature. So temperature is a reference to another concept in algorithms, especially in simulated annealing, where you have a general parameter that defines how likely test cases, or not test cases in this case, but how likely you are to change the probabilities or the search criteria or things like that. So over time, what you'd have is when you start the test run, all the percentages are equal and very likely to change. And then after 10,000 test cases or so, they're much less likely to change. So what will happen is over time, because things are less likely to change, you'll settle out to a 50-50 between our Java friends and C++ friends. So that would be something that if you see that thrashing, that you can put in there. It's not been something that I've necessarily had to do because I haven't run into one of those applications. So the conclusion is with an evolutionary approach, we can use traditional test populations, things that we use we know are effective today, to find flaws, but also benefit from from random testing and from a number of other advances in optimum security testing. Put it into a single framework where it will self-organize around being able to use the most optimal tests that we do today in order to test systems. Benefit to this approach, especially if we keep it blind, is that it's broadly applicable to a number of systems and test criteria, though of course we can always make it smarter, and you always should, depending on what you have at your disposal. But if we keep it blind, we do not require interactive control in the process being tested. The drawbacks is if we keep it blind, again, we will not have the smartest fitness criteria. And so we'll have to run it for a very long time, or longer than if we had all the information in the world, to actually have it come across an optimal test set. But again, if we don't have the ability and we have a lot of time, then that's not a necessarily bad thing. And then one thing that rubs a lot of people the wrong way is that in the end, we have test cases that are not optimal or comprehensive, just optimized. What happens after you run this? And this actually happens with a lot of new testing techniques that don't rely on static test sets that a tester spends several months writing. Is that, okay, I ran this. I ran it for a week. I ran it for a month. What did it find? What coverage do I have? People will say, did you test for cross-site scripting? Well, yes, the thing did test for cross-site scripting. Up to 17% of the tests were based off of that. Did you test for this specific thing? Well, you can never answer that. And that rubs the people a lot of times the wrong way. The big thing I would say in response is that there is no such thing as comprehensive testing, that we really need to do the best we can with the time we have to test, and that though it's a bit of a shift to think about being optimal in this way as what we should be doing, it's something that if you think about it for a moment makes sense, even if we don't have a set of static test cases. And we can also put very high probabilities on those things that we always want to run, like apostrophe for SQL injection, to make sure that for the most part they get in. So what I presented here